Morning, everyone. We're going to change gears just a little bit, not a ton, but just a little bit. We're going to go out of a different section today. So we're going to be in chapter 7 in the Orange Book. So this is going to be out of 7A. So if you have any questions or if you want to look at an example and pause this, just know that that's where I'm getting this from. So what we're going to be talking about today is we're going to be talking about this concept of direct variation. And so to do that, we're going to go over this scenario where gas or petrol is $3 per gallon. And so basically you've got the amount of gas here and you've got the cost. So like 1 gallon is $3, 2 gallons is 6, 3 is 9, 4 is 12. And so what I want y'all to notice is, so if you double X, if you go from 1 to 2, the price also doubles from 3 to 6. Or if you went from 2 to 4, 6 to 12. And the same thing, if you tripled it or quadrupled it, holds true. If you triple X from 2 to 6, it goes from $6 to $18. So this is an example of direct variation. And so we say, okay, these variables X and Y, or they can vary, or the variables can change based on the problem. They vary in proportion to each other. We say that they are directly proportional. So they directly affect each other. So two variables are directly proportional or vary directly if multiplying one of them by a number results in the other one being multiplied by the same number. So similar to how up here, if we multiplied X by 3, Y would get multiplied by 3. That is by definition directly proportional. So the way that you write this, if variables are directly proportional, you say Y is directly proportional to X. It's like 3/4 of an infinity sign. It's like a sideways ribbon almost. So we read this, if Y is directly proportional to X, then the equation here we write is Y equals K times X. We call this K right here the proportionality constant, or the constant of proportionality. And we'll look at that just a little bit in depth today. But this is largely what we're going to be using right here, is Y equals the proportionality constant times X. So the first example that we're going to look at here is going to be example 1 on page 165. So if you want to look there as well, you are welcome to. And so basically what we have is we have a table right here that shows the relationship between the side length of a square and its perimeter. So as a reminder, a perimeter of a square is you just add up all the sides, but a quicker way for perimeter of a square is just to multiply it by 4. So like with the side length here, with a side length of 2, that'd give us 2, 4, 6, 8, a perimeter of 8. 3 would be 12, 5 would be 20. And so what we're going to do is we're going to use a graph to show that P here is directly proportional to X. So I'm going to make a real quick graph here. We're gonna scale it. So let's see, 2, 3, 4, 5, and we're going to go by 5s here. 5, 10, 15, 20. So we're going to go 0, 0, 1, 4, 2, 8, 3, 12, and then we'll go 5, 20, and we'll connect those. In a perfect world where Mr. Price draws perfect graphs, that would go through all of them evenly. And so if you notice here, the slope of this line is to go over 1, up 4, has a slope of 4. That right there is our constant of proportionality. So if we wanted to write or find a formula that connects these two, find a formula that connects P and X, we'd say that the way that you find the perimeter here, we'd say P equals, you're going to multiply the side length, X here, by 4. We're going to say 4 times X equals the perimeter of a square. And so this is pretty similar to this, what we were talking about up here, except P just represents our Y. 4 was our constant of proportionality, and X was just our side length here. So we're going to look at a couple more of examples here, and we will keep it rolling. So we're going to look at example 2 on page 167. And so the information that we're given here, they tell us that P is directly proportional to T. And so they tell us that P equals 17 when T equals 5. And they want us to find T when P equals 60. So the things that we're going to write here, we're going to say T and P. They tell us here that when T is 5, P is 17. And they say that they want to know what is, when this is 60, what is T? They said find T when P equals 60. So there's a couple of ways to think about this. So the first thing here is what do we have to multiply by to get from 17 to 60? And it's not going to be a perfect number here. Actually, so let's see. 17 times X equals 60. So the value that's going to work there is if we divide both sides by 17. So the value that we get here that we have to multiply by is 60 over 17. That is what we're going to be multiplying by here. So as a reminder, direct variation means that if you multiply one variable by 60 over 17, then it's only direct variation if the other one gets multiplied by it as well. So what we need to do is say, okay, well, we're going to multiply 5 times 60 over 17. And whatever that is, if this does vary directly, whatever I get from multiplying by this, that's going to give us that missing one. So that's going to be 300 divided by 17, which is approximately 17.6. So when T equals 17.6, then we can say that P equals 60. And we're going to say approximately 17.6. So we rounded to get that answer. So then the next example we're going to look at, this is actually I picked a problem from your all's textbook to go over. So this is number 11 on page 167. And so basically Isabella here has drawn a scale diagram of her school. An actual length of 60 meters is represented by 3 centimeters on her diagram. And so what we want to do first is we want to find the proportionality constant and explain how that relates to the scale here. So we need to think about, okay, what are our two variables here? We've got the actual length and we've got the scale length here. And which one are we going to have to multiply to get? So when you're setting this up, you've got your two variables. So you need to decide which one you want to take the place of the independent variable and the dependent variable. So in my opinion, the independent variable is going to be the actual length here. So we're going to say A for actual, or you could use Y here if you wanted to, whatever you're comfortable with. And by definition, we're going to say the proportion, the constant of proportionality here, excuse me, times the scale number here. And that's going to be our equation that we're going to use here. So to find that, what we're going to do is say, okay, well, if the actual was 60 meters and we have to multiply K by it to get the, or we have to multiply K times that 3 to get there, well, what's the value of K going to be? So the value of K here is, so if it's 3 times K equals 60, that means that K is going to be equal to 20. And so if you wanted to think about this like on a graph, our gradient here would be 20, our slope would be 20. And so in terms of thinking about what that means is that each centimeter here, so 1 centimeter on this scale that they're drawing, is 1 centimeter is going to be 20 meters on her drawing. That's the scale diagram right there, is that 1 centimeter is going to be the equivalent of 20 meters in her drawing. So then one of the questions that we want to answer here, so is that if the football pitch is 110 meters long, how long is it going to be on Isabella's diagram? So when we write that equation there, we've got A equals K times S. And we need to think, okay, what information do we know? So we know the actual one here is 110. We know that K that we just solved for is 20, and we want to know how long it is on, how long it should be on her diagram. So to figure that out, we're going to say, okay, well, 20 times what will give us 110. To figure that out, we're going to divide both sides by 20. And that will give us 5.5 centimeters. And so we can also answer questions both ways with direct variation here. So if we know that the front fence is 15 centimeters long on her diagram, we want to know what the actual length of the front fence is. So we'll say we're still using this model, so K times S here. We want to know what the actual length is here. So we're gonna leave A as it is. We know K here is 20, and we know the scale length is 15. So we're going to multiply those two things together. So we've got A equals K times S. So the actual here is going to be 300 meters. So that is a little bit of an introduction to direct variation. So we're going to look at another couple of examples here, I think just 2, and we're going to explore it in just a little bit of a different context here. So we're going to go into section 7b, and so what we're going to look at is occasionally we'll be dealing with direct variation when there are powers, where there's exponents present. And so in many circumstances here, the variables we consider aren't always directly proportional, but there is sometimes direct variation between their powers or between their exponents. And so what I mean by that, we're going to look at the surface area of a sphere just as an example. I figured it'd be a more applicable example here because that's something that's a formula that we physically know. A here is not directly proportional to R. However, A is directly proportional to R squared with that constant right here, 4 pi. And to kind of show you all what I mean by that is that if you plug in some different values for the radius here to get the surface area, if you substitute in 1 you're going to get 4 pi. If you substitute in 2, you'll get 16 pi. 3, you'll get 36 pi. So here, R and A, they do not vary directly because you can't multiply 1 times 4 pi and get to, or times 4, excuse me, and get to there. If you multiply this by 4, you would get to there. But over here with R squared in A, if you multiply by 4, you're going to get to the next step. So here we say that A varies directly with R squared. A, however, does not vary directly with R. And so we're going to look at 2 examples with that, and then we will call it a day for today. So the first one that we're going to look at, this is example 4 on page, or example 3, excuse me, our 4th example today on page 168. And so we've got this equation here, y equals 2x cubed divided by 7. And so what we want to do is state the 2 variables which are directly proportional, and then we want to determine that constant. Now, here, y and x aren't going to be directly proportional because there's 3 x's here. It's x cubed. It's x times x times x. So we're going to just say y is directly proportional to x cubed right here. Y is directly proportional to x cubed right there. And so now we have to say, well, okay, well, what is in place of k for us here? What is going to be multiplying x cubed every single time right here? And the answer to that, you should be saying to yourselves, well, there's that 2/7 there, Mr. Price. There's technically a little bit of division in it, but as far as it being in the form of y equals kx, we're saying that x is effectively the same thing as x cubed here for all intents and purposes, and we're saying that that k right there is going to be 2/7. So that was all that we had to do for that problem. Is just say which 2 variables are proportional directly, and what is that constant of proportionality. Now, the last one, we will actually do a little bit of math here. So we're going to look at example 4 on page 169. And so what it's saying here, suppose D, some variable D, is directly proportional to z squared. And that when D equals 14, or D equals 14 when Z equals 5. And we want to find D when Z equals 15. So I'm going to make a table here real quick. So let's see. Z is 5 when D is 14. And we want to know what happens when Z is 15. And we're going to put a question mark right here. Now, the thing that we've got to understand here, there is multiplication by 3 right here. They from 5 to 15, those are being multiplied by 3. But the thing that is directly proportional here, D is directly proportional to Z squared here. So when Z gets multiplied by 3 here, that means that what's really happening is Z squared is getting multiplied by 9. If Z is multiplied by 3, Z squared is multiplied by 9. So we need to recognize that that is happening, because what we're going to do is not multiply D by 3 here. We're going to multiply D by 9, and then that will tell us what the value is here. So let's see, 14 times 9, is going to give us 126, and that is the value. When Z is 15, that would be the value of D, 126. 126. So we have to pay attention to those exponents here, because even though the table is in Z, we said D was proportional to Z squared. So then we're going to look at another one here. In the words of the wise DJ Khaled, he always said another one. So I'm going to honor him with this last example. So let's see here. They say we still have this condition when Z is 5, D is 14. And we say that we want to find Z when D equals 140. So we're going to put a question mark right there. And so let's see here. D got multiplied by 10 here. And we want to try to figure out what Z is based off of that. So if you were going to write a equation model for what we are writing here, we would say that D is equal to K times Z squared. And this equation model would very well work for the first one as well. I wanted to show you all two different ways to do this. So if you're like, Mr. Price, why didn't you use the equation on the first one? I'm trying to make us versatile. So the definition of directly proportional is that your two variables in question, if you can multiply it by K, it should be equal to D. So with those two variables there. So let's see. We know that D here is going to be 140. But we did not figure out what K was. We did not figure out what the value of K was. So we need to do that real quick. So in order to do that, we've got to say, okay, we need to figure out the value of Z squared. So we're going to go back to the previous problem just real quickly. And the point we're going to use to do that is going to be this 514. So D is 14 when Z is 5. So we're going to say K times 25 equals 14. We're going to divide by 25. And that's going to give us 0.56. That's our proportion constant right there. So now I'm going to take this sucker, substitute it in right there. 140 equals 0.56 K, or not K, just 0.56, excuse me, times Z squared. And now we need to evaluate for it. We need to solve for it. So we're going to divide both sides by 0.56 here, 0.56. And let's see, 140 divided by 0.56, that is going to give me 250 equals Z squared here. And so then to solve, we're going to take the square root of both sides here to get that Z is approximately 15.8. So we're going to say that Z equals 15.8 when D equals 140. And so that is all of the notes that I have for today on direct variation. If you all have any questions on direct variation, please shoot me an email. Let me know through Zoom. We can set up a time to go over some of this. But if you all have any questions, please let me know. But y'all have a good day.